All right, so good afternoon, everybody, and welcome to another exciting broadcast with us here at Exploring by the Seat of Your Pants. I know we've got a lot of familiar faces in the crowd, but if you are new to us, we are all about bringing conservation, adventure, and science into classrooms around the world. And today's program is exciting for a multitude of reasons. Number one, we continue our epic entire month of February dedicated solely to incredible women in science and exploration. This is classically our biggest month. We get the biggest audiences, and it's such a thrill to have you back as we are highlighting some of the most amazing female explorers, scientists, conservationists around the globe. Thank you all so much for joining. Today alone, we've already talked with Justine Hudson about whale research in Churchill, Manitoba and across the Arctic, and with Jessica Carrera, who's a veterinarian with Ewaso Lions live from Kenya. We're going completely opposite to those two topics with our third speaker today, but we'll get to that in just a second. Now, today marks the beginning, too, of a really exciting series in conjunction with Western Space. They do such great work to engage the public with the world of exploring the cosmos, whether it's robotics, artificial intelligence, space exploration. Generally, we've done dozens of programs with them over the year. We've got a very special series starting with them today, specifically with Mission Control Space Services, one of our multitude of partners in this really incredible series coming in the months to come. Now, without further ado, I'm going to turn it over to Vanessa Van Decker, who is almost one of the only people who's as enthusiastic as I am, which is really exciting. Before you got underway, I got the chance to chat with her a little. So you're in for a treat today, and she is going to walk us through some of the incredible stuff happening in robotics and space exploration, moon, artificial intelligence, some of her own work, and more. I hope you're as excited as I am. And without further ado, Vanessa, welcome to your first Exploring by the Seat of Your Pants broadcast.
Thank you so much. I'm so happy to join you all today. Thank you for coming. I'm Vanessa, and I work on space robotics as a mission operations engineering intern. I'm also a mechanical engineering student at Toronto Metropolitan University. And today I want to tell you a little bit about how I got to be working in space robotics and what even is space robotics, because I think it's pretty awesome. So I grew up in a small town called Palmer Rapids in the rural Ottawa Valley on the Madawaska River. That's the Madawaska River there in the background. I've always really loved creating something new and building things, whether that's a snow fort, knitting a hat, or building a robot. In grade 12, I fell in love with mechanical engineering because I got the opportunity to join a robotics team. And you can see there on the left, that's me in the red sweater with my first ever robot. It was a robot that could drive around and pick up balls there in the elastic bands and shoot them out at targets. It was pretty awesome. But that robot took me 10 tries to make it work. I built it, took it all apart again, built it, took it apart again and again until it worked. And I loved that process. It was frustrating, but super rewarding. And I knew that engineering was for me. I wanted to learn how to create complex machines. And I also loved nature growing up, especially the night sky. I loved going swimming in the river at night with my mom and feeling like I was floating in space with the stars above reflected down on the still water surface. I still feel that wonder when I look up at the sky full of stars, or when I watch a rocket launch or a rover exploring another planet. There in the middle, that's me with my Mars rover on my university rover team. And then on the right at the top, that's a part that I made for our rover on the lathe, which is a fancy machine that you use to make metal parts for robots, which is very fun. And on the bottom, that's a cardiac catheter robot that I worked on for heart surgery. So robots can do so many things. I'm currently working at Mission Control, headquartered in Ottawa, Ontario, Canada. Since I'm a full-time student studying in Toronto, I'm working remotely. That's why I'm coming to you from my living room. But I get to work with this incredible team that's in Ottawa. And here you can see a little bit of our office. So there on the bottom, that's a map of our moon yard, which is pretty incredible. It's like an adult-sized sandbox that I get to work in. You can see the moon craters and huge boulders. It's really big when you stand inside of it. You know, I could probably lay down in one of those craters. I actually created that map with the drone that you can see at the right there, sitting on top of our lunar rover. And you can see on the left, the lunar rover driving around, making tracks in the moon yard, kind of gives you a sense of scale. Our team at Mission Control is pretty awesome. It's made up of planetary scientists, engineers that have worked on NASA projects, AI specialists, and so many incredible experts that come together to bring their strengths to the team. Another amazing thing is that the team is made up half of women, which is really unusual in engineering. Sometimes as a woman in STEM, you might be the only one in the room, or you could face barriers where people don't believe in you and your capabilities. It's so nice to work in such a supportive environment with so many brilliant women. In mechanical engineering, we study how things move and how we can build machines to accomplish goals. A lot of people think of engineering as a very logical pursuit. And while engineers do rely on math and logic, it's also deeply creative. Creativity isn't only about thinking of the most out there and innovative solution, it's also about asking really good questions. In fact, a lot of times the simplest solution is best, but if we don't start from a place with a wide open mind where we think, what if? And we try and look at a problem from all of the possible perspectives, we won't find the best solution. Mechanical engineering encompasses a lot of things. So sometimes people ask me, why robots? Well, I think robots are so cool. They can help us do incredibly challenging things because robots are really tough and they can be built especially to be the best at a specific task. For instance, humans can only see in some wavelengths of light, but we can make robots see in whatever wavelength we want as long as we have the right sensors. Another cool capability of robots, you can see down there in the bottom right, is this robot. That's the view from the camera on our lunar rover. So it's kind of like the camera, the rover eye view. If you were the lunar rover, that's what you'd see. And if you see those lines, it says 1 meter, 2 meters. So just by having that in our camera, we can see exactly how far away a rock is. We'll know how far it takes to get there, which can be really important, for instance, when you're on the moon, because we don't have a sense of scale. There are no trees to tell us how far away is that thing I see in the distance. But with a robot, we know exactly how far away it is. On the bottom left there, you can see some really cool robots. That is the Orbital Autonomy Lab that I've helped set up at Mission Control. We have 2 robotic arms and the Lunar Gateway model. The Lunar Gateway is a really cool space station that we're building around the moon right now. So I was saying that we can build robots to see in all kinds of different wavelengths, which is super powerful. Another cool example of robots being really powerful is this summer, I got to mount a laser-induced breakdown spectroscopy unit, or LIBS for short, on our lunar rover at Mission Control. The LIBS has a really strong laser, and you can see it down there in the bottom right. It's like silver and black in front of the yellow rover. And we shoot it at rocks, kind of like the ones you see in that top picture with our geologists at Mission Control, Mel and Cosette. So we shoot it at those rocks, and it literally vaporizes them. It's so awesome. And it makes a really cool sound. It goes pew, pew, and burns away a little piece of the rock. The robot can then read the vaporized rock and tell us from the spectrum of light it produced what elements the rock is made of. Kind of like reverse engineering the recipe to make that rock. Pretty cool. We need robots to be this kind of sidekick to astronauts. They'll explore ahead of us and keep everything running when the astronauts come back to Earth. Robots are one of our best tools to explore outer space. They're really tough, and they have lots of cool technology that we can use for exploration. And they don't need to take it back home to Earth. Here you can see a couple of robots in our Orbital Autonomy Lab simulating what might happen in orbit around the Earth when we're tracking a satellite. This is the robot's eye view looking over the gripper, which is kind of like the hand of the robot. At Mission Control, I get to work with 2 robotic arms, and they're called Ada and Atlas. So the one with the satellite on it, that's Atlas, and the one with the camera on it, that's Ada. We use these robotic arms to simulate the conditions of working with robots in orbit. We can work on a space station with them, like the Lunar Gateway, or work on satellites like this. When on my second week of work at Mission Control, 2 robotic arms arrived in the office, it was like Christmas, because I love robots, if you can't tell. I had a lot to learn about them, and I was tasked with becoming an expert on the robotic arms, learning what they could do and how we could control them. I even designed a model of the lunar gateway for the arms to perform missions with. If you look at robots in orbit, the light is really harsh because there are no clouds or atmosphere to disperse the light. So I designed clamps to hold up these super strong lights in the lab to simulate the sun. These analog conditions, like lighting being really close to what we see in orbit, is super important so that the camera feed like this that we then use to develop our software is accurate. The part of the robot that you can see, the part of it like its body, that it's moving, all the nuts and the bolts and the cameras, that we call hardware. The part you can't see is called software, and that's like the brain of the robot. Mission Control, where I work, specializes in robotics software. Software engineers can use code to make robots intelligent, capable of making decisions. Have you ever heard of artificial intelligence? We also call it AI. AI is when machines and computers can learn and think like a human or animal would. Tesla uses vision recognition, AI, to identify things that are in front of its autonomous cars. At Mission Control, we've developed MoonNet, which is an AI that identifies important geologic features on the moon. I think here it is. So you can see on the right there, the pink is the boulders. And then we have crater interiors, which are dark purple. And then you can see the crater exteriors turn green. And then the sand is yellow, which on moon we call dirt or sand regolith, because it's actually very different than the kind of dirt we see on Earth. It's really sharp and jagged because there's no water on the moon to erode it, and has a lot of different characteristics. Sometimes it contains glass from micrometeorite impacts. Anyways, I can go off and talk about regolith all day. Regolith is really cool. But what the computer AI does is it segments these pictures we take of the moon into components, and it becomes a really great sidekick for planetary geologists. These are just some of the objects of interest that it can recognize. And I actually got the opportunity to write the mission operations manual for MoonNet. It launched in December on a SpaceX rocket, and it's currently on the way to the moon. You can see in the center picture there, the blue line is how far it's already gone on its journey to the moon. And that's from Tuesday. That's exactly where it is. It still has a way to go. It's going to trace that path around until it reaches the moon. The moon is the little dot in the yellow circle. That's the moon's orbit of the Earth. And then the larger blue dot in the center is our home Earth, where the rocket took off from. AI is meant to not replace humans, but to help them. When we're in a lunar mission, we have a really limited amount of time to do a lot of science. A lunar day lasts 14 Earth days, and a lot of missions aren't designed to survive beyond that because the lunar nights are very, very cold, even cold for robots. That means all of the science that you've worked on for years and years to accomplish has to get done within 2 weeks. That's a really high pressure timeline for the science team and the planetary geologists. MoonNet is going to be the first ever AI on the moon. And on the left, that's the lander that it's going to be on. It helps geologists identify important features of interest and helps them plan what they want to do with that special, precious, limited time, because they can only see and inspect so many rocks, so they have to pick their priorities. AI is also really important for orbital robotics, like the robotic arms I work with. We use this orbital autonomy lab to train computers to work and think and recognize satellites, for instance, to help to be able to plan a path to intercept and capture space debris. Has anyone heard of the International Space Station? The International Space Station is flying around the Earth right now at 27,580 kilometers an hour. That's way over any speed limit I've ever seen on Earth. It has 7 astronauts currently on board doing science. The International Space Station was actually built with the first Canadarm that rode aboard the space shuttle. Canadarm2 lives now on the International Space Station and helps do repairs, scientist tasks, and other important maneuvers outside the ISS. In the top left, that's the ISS, or International Space Station, right there with the arms sticking out below it like a V. Astronauts can even buckle in and ride on the end of the Canadarm when on a spacewalk, like you see in the center. That sounds like a pretty great way to get around, if you ask me, and the view is incredible. You can see the Earth below you. Humanity is building a similar space station that will orbit around the moon, which is in the top right. That is an artist's rendition of what the lunar gateway might look like when we build it. This space station will have astronauts on board sometimes, but when the astronauts come back home to Earth, it will be entirely controlled by the flight controllers here on our planet and the robots that we leave behind to take care of the station. It's also going to be built and maintained by Canadarm number 3. The Canadarms are super cool because they can walk end over end, kind of like this. They walk like this. They flip. Let me see. I'm going to use my TV remote. This is like the Canadarm, pretend. And it connects on both ends, so it can flip along the space station. It has like a hand on either end, flipping along to be able to travel along the space station like that. It's pretty cool to watch. Actually, I mentioned before that our robotic arms are called Ada and Atlas. Well, Ada is a twofold name. It's named after Canadarm, but also after Ada Lovelace, who was the first ever computer program. Ada wrote the first ever computer program. At that point, computers didn't actually exist, but there was a plan to build the first ever computer, and she was the one who figured out how important computers could be, how we could do really complex mathematics and solve really complex problems by setting a set of logical instructions to the machine. Atlas is named after a mythological person who we tell the story about him holding up the heavens, which is very appropriate for a space company. And this is our stronger robot of the two. Atlas we use to hold our satellite and simulate the motion of a satellite tumbling in orbit. You probably know how important it is to keep our Earth clean, to clean up your garbage and recycle. But did you also know it's really important in space? Space debris is a huge problem. In the bottom there, you can see how bad it's getting. In 1957, we didn't have a lot of space junk. We hadn't sent a lot of things to space. But now, as we send up more and more satellites and spacecraft, and we don't worry about cleaning up after ourselves, it's getting really dangerous. When things are in space, they're going really fast along the Earth. And when the satellites that are no longer operational and they're not being controlled or functioning collide with other space debris, they break apart and create even more space debris. This is really bad for our space environment and could be dangerous to astronauts if their spaceship collides with it, but our robots can help. Robotic arms like the ones you saw can be used to approach spacecraft and bring them back down to Earth to clean up our orbits. Once they're brought down, the debris will safely burn up in the Earth's atmosphere. Space debris is a really big future problem and one we haven't totally solved. It's something that you could help with in your careers. All right, to finish off, before you ask me some of your amazing questions about space robots, I'm going to show you some DiscoBot Boogie. When I was first working with the robotic arms, I needed to design a testing sequence. So I thought, why not teach it to disco dance?
Vanessa, that's a pretty fun thing to do with a robot. I gotta say, my robotic talents are much lower than yours, but that's a good gig. By the way, the whole idea of a ball shooting robot, the first robot I ever saw in my life was in my high school. I had a person that was like you that could just put together anything with like a toothpick and a pocket knife, and the robot was just going around the hall shooting volleyballs at people. And I'm sure the teachers appreciated that very, very much.
It's a very fun robot to make. You know, it's endless. What other things can you shoot with a robot?
Bigger balls. I have a moon globe back there. We could shoot the moon at people and then like teach them about space all in one
water
go.
Balloons.
This is the dream. Vanessa, this has been so much fun. And as you said, we got tons of time for questions together. So I'm so excited for our YouTube friends. If you guys want to share any questions, come to you there. Please feel free to type in the chat anything you're keen on. And we'll head to all our live classes to see what questions we might have from all sorts of students. So Mr. Hancock in Georgetown, Ontario, if you guys want to kick us off, I'll head to you for our first question. If you're there, where'd Mr. Hancock go? Where is he?
Oh, no, we're just cleaning up from lunch, Jesse. You know I'm here.
Oh, I know you're here. There you go. Hey, man.
Yeah, we were wondering, there must be a fair bit of failure and frustration in your job. We talk about making mistakes as learning opportunities.
Mm-hmm.
What's that frustration like, and how do you not give up?
Great
Yeah,
question.
I think that's an amazing question. Thank you. Well, I think that one of my best strengths is actually tenacity. And I think that can get you so far. I think it's not about doing it right. It's about doing it again and not giving up, like you said. So failure is part of the design cycle that we learn in engineering. And it's better to build something and break it and build it again than to try and make the perfect thing. So in engineering, we like to make a hypothesis about a way we could solve a problem. So first we look at the problem and we say, okay, what exactly is this problem, which is an important step. Make sure we actually understand the problem. And then we pick some designs that we could use to solve it. So maybe like 3, I could do it this way or this way. So maybe, for instance, a claw, like you want to pick something up. So you could pick it up by squeezing it between 2 hands, kind of like this. Or you could have 3 fingers that pick it up like this. And you're trying to decide which is better. So you look at those options and then you decide, okay, I'm going to build it. Sometimes the best way is to try building both and test them. But maybe you only have time to build one. But either way, when you build it, that's not going to be the end. Then you're going to make it again, because that's where we learn. We learn by it not working, and then we know how to make it better. So I'd urge you to look at it failing as an opportunity to make it better and to learn. And it's actually exciting because then you know where you can improve it.
I fail all the time in these broadcasts. I say the wrong line, I forget to send the link, and I consider that a learning opportunity too. So that's a great message, and thank you for that question, Mr. Hancock. Very thoughtful to begin. St. Ambrose, grade 5. If you guys want to unmute your mics, I'll come to you for our second question. A note to all our teachers: you can all unmute your mics. When you're in the background, I can't hear you till I want to, I promise. But grade 5 crew, if you want to come on up, yeah, come and unmute though. Hi, yes, you are on camera. I know. I'm excited too every time. But yes, unmute and you're good to go.
Hello.
Hello.
Hi, yeah, we have a question. So we're doing a big coding project, and that's why we wanted to come on and meet you today. We want to know when you mentioned earlier that it took you 10 times to build your first robot, and we just want to know what kept you going and not wanting to give up, and how did you fix and find your mistakes, and what was that process like?
Yeah, I think that is huge. I think trying it is the biggest thing. And some of my mistakes were pretty obvious. It would fall apart. It would be like, okay, that is not a strong enough way to build it. Or I also was working on coding like you guys are and trying to figure out how to get the ball to shoot. And, sometimes it just was, that code doesn't work. That's getting it too close to the target. And I knew it was too close because it was either going like too low. It didn't have enough room for that arc of the trajectory to get high enough to the target. So I'd say testing is really important to see your mistakes. Sometimes with coding, it's hard to see the bugs or the mistakes because, it's like a comma or just the wrong word you put in. Sometimes what I'll do is I'll read it backwards because I'm so used to reading it forwards. If I read it backwards, it's easier to see my mistakes, tricks like that. But you've got this. I'm so excited to hear you guys are making those projects.
I'm so fascinated with these first two questions because they're so unusual compared to the sort of questions that I would have expected going into this. So thank you guys for throwing me off here. Miss Pereira, grade 3's Gems World Academy. If you guys want to come on in, you're good to go. Hi, Chicago. Hi. Hello. I'm excited too. Do you have a question for Vanessa? Yeah, you're good.
How long does it usually take to code and send the robots to space?
Nice.
It takes a really long time to send things to space. Some missions take less time, but it always takes on the scale of years. So some missions might take 2 years, but a lot of missions take 10 years. Some people work on missions for their whole careers. James Webb Space Telescope, which is pretty awesome. I don't know if you guys have seen some of the amazing star pictures from James Webb Space Telescope, but if you haven't seen JWST, highly recommend. And that went up last year, and I think that was worked on for something like 3 decades, so like 30 years. That one's exceptional. That one was a very long project, but some people spend their whole careers on something really big and fantastic like that. There are also smaller scale projects, you know, that can take 1 year or 2 years and get to space, and it's really exciting.
Yeah, I love the nuance there, and it's something that, again, seems a little shocking to spend a decade of your life. I mean, our students today, some of them are 10. So think about your entire life on one project, and it's like, wow, I'd like to do other things, but you're getting to work with all sorts of people from around the world. You're getting to put your skills and expertise to the absolute test every day, and then you get to see it come to fruition with something like the James Webb Space Telescope, and it changes the world. I mean, like, it's the greatest scientific implement that we've put up in decades, and it's so transcendent to see how people respond to those images and that science, and that's a pretty special thing. Very few people in their careers get that sort of impact where they get to see it come to fruition like that. So that's sort of a benefit of engineering and robotics, which is really exciting.
And a really great thing is nothing goes to space by one person. Everything is a team effort, and you have to have that team of experts where everyone's really good at the part they're working on. So you don't have to know everything. You just need to know some things really well. And it's really great to be able to lean on your team. And for those really long projects like that, maybe you're not working on it for the whole life cycle of it, but you have a really key contribution that you get to be a part of. Like the MoonNet AI that's on the way to the moon right now that I worked on. I just started working on it in July, and it launched in December, but it had been worked on for a long time before that by other people who are really amazing. So I was so lucky to get to contribute to it, but it wasn't a one-person project, or, you know, that was just one little bit of it.
Yeah. Fantastic, Vanessa. I'm going to head to Miss Carter and Miss Buckley's class in just a second live, but I love this question from YouTube. So from Mr. Vago's class, grade 6s at St. Simon in Toronto, they want to know, are there robots on other planets outside of the Earth? Yeah, tell us more.
Yeah, there are so many cool robots. You know, we have robots right now on Mars, like the Perseverance rover, and we're sending robots to the moon, which are so awesome. But we also have robots going to icy worlds in our solar system, where they're going to explore the interface between water, because we know a lot of life likes to live in water. So there's a lot of cool NASA projects working on that right now that haven't launched yet, but that are going to be so exciting. We've also sent some robots to orbit around gassy planets to inspect them. So, you know, the sky is not the limit. The universe is so many places that we have yet to explore with robotics.
I tell this to every student every time we do a program on space. Like, this is the most exciting time to be interested in space ever. The only comparable time was like the Apollo missions when we were first going to the moon, but we're going back to the moon. We're looking into Mars. We've got robots all over the solar system. There's more investment and excitement. There are way more countries involved that are doing amazing things right now. Like, it is, if you are interested in being an engineer, a science communicator, an astronaut, whatever, like, go now. Like, this is the best time ever. You kids are so lucky because you're going to grow up. Kids these ages are going to be the people that walk on Mars, which is pretty cool. You mentioned icy worlds. I want to encourage our classes to look up Europa and Enceladus when you're done these programs. These are the two moons of Jupiter and Saturn, respectively, that are just really, really special places in our solar system that we're looking possibly for signs of life. Certainly, we understand that there's water, there's oceans on these places underneath their icy exteriors. So they're really exciting places for inquiry if you guys are keen to follow up and learn more. Miss Carter's 5-6s, come on in and take us away. Unmute your mic. You're good to go. Hi.
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 What was your favorite project that you made?
Ooh, no
My
pressure.
favorite project. Well, I mentioned in passing, it's really hard to pick a favorite, but one I didn't get to tell you a lot about is I worked on researching lunar dust mitigation strategies using electrostatic methods. So this was a really cool project because, like we said, we're sending lots of robots to the moon. And with that, we have to think about how are we going to handle lunar dust? Lunar dust isn't like dust on Earth. It's super sharp. It's like glass. And it's also sticky because it's charged. It's electrostatically charged. So it wants to stick to you. So you have this dust everywhere blowing around on the surface of the moon that wants to stick to you. And how are you going to handle that? How are you going to make sure that your solar panels don't get covered in it, or your cameras, so you can do your science? So it's a really cool problem that a lot of engineers are working on to solve. And I really enjoyed that.
I bet. What a cool story. I remember when they first landed the Apollo 11 on the moon, they were kind of concerned, this is a huge vehicle. Will it sink? They have these big pads on the feet to make sure that, okay. And it didn't quite sink down the way that they sort of feared it might, which is the moon's a special place. Let's face it. And I'm so glad to see that we're heading back pretty soon. It's pretty exciting times. Miss Buckley's class, we're going back to Toronto, my childhood home. We got all the Toronto classes today for you, Vanessa. But come on in, guys, and welcome to the broadcast. Hi, everybody. So
Hi.
yes, if you have a question for us, come on up. Anyone who wants to ask, you're good to go.
What was like, how did you know you wanted to do this when you how did you know this is the field of whatever you wanted to do?
Yeah.
Yeah, it's really hard to know what you want to do. I thought maybe I wanted to be a doctor. I thought I might want to be an artist. I really like a lot of things. I loved science, but I also love writing. I really love creative writing. I really love art. But like I said before, I think of engineering as very creative, which makes it really exciting for me. I still feel like I get to use my creative juices to solve these cool robotics problems. And I find robotics is especially creative because, I get to build something that's going to make this impact. I think the best way to find out what you want to do is to try a lot of things. So I didn't ever try robotics until grade 12, and I wish I'd found it sooner. And once I tried building robots, I realized, wow, I really want to do this. I started taking my robot home and working on it at night, and I just was so excited to solve these problems and keep building it and keep trying it. And I didn't want to stop. And I had this epiphany that, oh, this is something I'd be really happy to work on for a really long time. I can see myself doing this. So that's what happened for me. So I'd say try things, and maybe you'll find that thing you love that really lights you up like it lights me up.
That's what I was going to say. This is the second time today we've gotten this question, and it's really interesting because I think a lot of people presume that people that are as passionate as you, they were 4 years old and you loved it and that was it, and you said 99% of the time that's not the case. People discover it whether they're in middle school, high school. When I was in university, I knew I was one of those lucky people that knew what I wanted to do from when I was very young. But I know people that are in their mid-30s that still don't know what they want to do. That's okay. As Vanessa said, try as many things as possible. And when you hit something that really you just want to do it constantly. Maybe you have a hobby in your life right now that's just fascinating to you. Maybe it's reading, maybe it's drawing. Those things can become careers and something that you make a living at, that you get to do in a professional context. And so follow what you're interested in. It sounds so trite, but it's such a powerful message. So I'm really glad we got that question. Very enthusiastically stated question too, by the way. So thank you to Miss Buckley, student. Vanessa, you were one of the fastest Q&A people ever. So we have time for one whole other round of questions, which is great. YouTubers, please feel free to share there as well. But we're going to head back to Mr. Hancock's group. Do you have another one for us? Come on up.
Oh yeah, definitely, always. We had one of our students were wondering, have you ever been on a project and you've just had to, it got scrubbed, it got canceled, it didn't work out, it ended, it wasn't going to work out?
Yes. This has happened. It happened to me with my university robotics team, and we had one idea of how we wanted to test soil samples to determine whether there was life in them. So that was one of our our jobs on a robot when we were going to competition to take soil samples and tell the judges, is there life in this soil sample? And we had a lot of ideas of how we wanted to do it. And the best, most reliable way would have been to use spectroscopy with like fancy equipment, but we just couldn't afford it. We tried to get grants from the university, and a big constraint in engineering is budget. So we didn't get to go ahead with that, but we ended up finding a really great solution. We had some amazing chemistry students on the team, and we used some chemical reagents to identify proteins and DNA in the samples, and it ended up being really successful and maybe more reliable than the fancy solution. Sometimes those constraints come to creativity.
You also highlighted something that I always love featuring in scientific conversations, and that's the fact that you get to work with so many different people of different disciplines. Like, great science is like an engineer with a chemist, with a biologist, with a engineer, and you never know what can come from that. Like, that's a fascinating thing in great scientific enterprises and creative places. Like Disney's a good example of that, National Geographic, where you have these people that get to work together because no one knows everything, and that's okay, but you get to collaborate and make some really special things come to life. So great question, guys. St. Ambrose grade 5s, your stuff's off, but if you want to turn your devices back on, if you'd like a second question, I will come to you in a minute. I'm going to head to Chicago first, our grade 3 class, for another to begin. Hey, guys.
No. Could I go after? When was the first time you sent a rover to Mars? Which year?
Well, I haven't sent one yet. I would love to do that one day. That's super awesome. When was the first one sent? I think the first one was Opportunity, or was it Sojourner?
I think Sojourner beats Opportunity, because Opportunity's with Spirit, and they're the duo. Sojourner's much less. I'm trying to figure out, first robot to Mars.
Trying to remember my robot history here.
Yeah, they have, when you look it up, Pathfinder's 97. When did Sojourner? See, this is so early.
Landed December 1996 in Mars Aries Valleys.
That's amazing, though. Sorry, I'm going to harp on this, because for our kids, I know if you're like 7, 96 seems like an eternity ago, but it's not. I was born in 92, so that's very recent. Like, Mars exploration is so recent, and we've sent so many incredible missions there. So again, if you're keen on Mars, you can go online when you're done this program and look at live footage from actual robots on Mars right now. That's amazing. I also really encourage our classes. Goodnight Oppie. Vanessa and I were talking about this beginning. Fantastic documentary on the engineering behind some Mars robots. So do check that out when you're done. It's just a really special learning opportunity. Vanessa, I'm going to head to Miss Carter's 5-6s if they've got another question for us. I know they do. They're right there. So come on in, guys.
Hello.
Hi.
Do you know any other engineers that went to space?
Ooh.
This is a great question. Well, a lot of astronauts are engineers. I don't know if you guys have heard of Chris Hadfield, but he's an aerospace engineer. I think our current Canadian astronaut, Jenny City Gibbons, is also an engineer. A lot of astronauts have been engineers and have gone to space. It's actually a really great way to become an astronaut. For me, that's not my goal. I don't see myself as an astronaut. I just want to send really cool robots to space. But some people, that is their dream, to become an astronaut. And one of the best ways to do that is to have really strong skills, because when they put together a team of astronauts, they're putting together a team of experts. Now, engineering is not the only way to do that. You can be an expert astrobiologist, which is a biologist who works on outer space, which is really cool. Or you can be an expert geologist, or a doctor, a lot of doctor astronauts. But it's really good to have those kind of skills that you can bring to the team.
Yeah. We have 4 astronauts in Canada for our Canadian crew right now. So we've got David St. Jacques, who's the only astronaut that's been to space of our current 4. We've got Jeremy Hansen, Jenny City Gibbons, and Josh Kutrick. So with you talk about skills, I always like highlighting this. David St. Jacques, who's, again, our one that's been to space, is an astronaut, engineer, astrophysicist, and medical doctor. Like, he's like, I don't even know how you can pack that much into an early life, but it's a really incredible story if you want to look him up. Vanessa, time flies and you're having fun. We've got time for one more question live from Miss Buckley's class, and we'll wrap up after that. So come on in, guys. Welcome in.
Hey.
Hey.
Our last question has to do with part of your presentation. You talked about the fact that there's lots of space garbage and it's building up and nobody really seems to care. And that's kind of part of the solution, or like needing to look for. But I guess kind of why does nobody care? And like, was there not a way to build in planned obsolescence to the satellites?
Good phrase. I haven't heard planned obsolescence in like 5 years. Thank you for that.
This is such a great question. And now there's a lot of people saying exactly what you're saying. Why does nobody care? Originally, when we were sending things to space in the 1960s, 70s, even as early as the early 2000s, we thought space was kind of unlimited. You know, in our naivete, people looked at space and it seems like there's so much space in space. It's so big. But actually, you know, there's only certain orbits that really work for having satellites. And you know, it's a finite resource. There is only so much space around our planet, even though it seems so big. So we're now realizing how important that is. And a lot of that's going to have to come down to space policy experts and politicians getting international collaboration. You know, international collaboration is so big for space exploration, but also it's expensive to fix space garbage. You know, companies don't want to pay to take down their satellite that no longer works. But hopefully now that we're all seeing it as such a big issue, it's going to become the norm and companies are going to be required to take care of their defunct spacecraft and nations as well. Hopefully we can come together as a planet to help solve this big problem.
There's a term for this. I mean, the tragedy of the commons is literally a phrase. It applies to the ocean. It applies to our lands on the earth. It applies to space and space junk. I have linked in NASA's whole article on space junk if you want to check that out as a resource to follow up with. But it's something where you need regulation. You need there to be government bodies or international bodies that say, look, you can't do this without this sort of thing built in, because here are the problems that really could impact all of us. So I'm really glad we brought this up. You could have many whole presentations on the space junk issue, so I'm glad we brought it up at the end. But Vanessa, I'm going to highlight a few things for classes to check out when they're done this program. I'll link them all in an email as well. But again, this is all because of a collaboration with us and Western Space. So a big thank you to them for coordinating the series. Mission Control Space Services, if you want to learn more about Vanessa's amazing organization, some of the cool stuff they're up to. If you're a student and you're keen on the exploration and development of space, check out SEDS. Vanessa, you're the head.
I'm the president of SEDS Canada. I didn't even get to talk about it, but if you want to do student research or even volunteer, you can even volunteer if you're a student with SEDS Canada. And it's a great organization to meet other people who love space and work in the space industry.
Fantastic. And then two other quick things. The pathway, you talked about this as being a big avenue for you to learn and get involved in the space industry. So do check that out, students. It's a little older than most of our students today, but really worth checking out. And you're one of the few speakers, thank you, to be willing to do this. If people want to check you out, ask questions, bug you on Instagram. She's on Instagram at Vanessa Van Decker. Very easy to find. I hope you take that chance. Vanessa, before I wrap up and bring our classes in to say a big thank you and farewell, is there any final message you want to leave our students with today about this field, about your own passion, anything to cap us off?
I want to tell you that you don't need to be an expert to start. When I started with robotics, it was really intimidating. I walked into the shop, everybody already knew how to use the tools, and I didn't, but I learned how to use them just by trying and trying again. And don't give up. Keep that tenacity. And that's how you'll get to build the really cool things in your imagination, that you can get there.
Vanessa, there's no better message than that. Thank you so much for joining us for the first time. We've got such great feedback on YouTube and StreamYard for this. You are a truly charismatic, fantastic advocate for space, and it's been a real pleasure having you. What we do to end every broadcast, I'm going to bring in our classes that didn't have to dip off for lunch. So Mr. Hancock, Miss Buckley's class, come on in and join me. Thank you so much for being here. Thank you, everyone. Have a wonderful day. Bye for now, guys. Thanks so much.